Hi, we're FH16, Joint Communication and Sensing version 2. I'm Toby Sohn.
I'm Jose Olmedo.
I'm Gerald Liu.
I'm Robert Scott.
I'm Brian Ding.
I'm Rafael Lee.
This video provides a full history of the work done on Joint Communication and Sensing version 2 and thoroughly explores the background, planning, implementation, evaluation, and analysis of the whole process.
The goal of our project was to implement a bi-radio test system that connects two ends and refactor the system to run through a GPU. Since the radio spectrum is shared by many devices, this project was inspired by the need for primary users to require unobstructed access while secondary users use available space. The project aims to develop context-aware communication systems using radar and to minimize interference using a reinforcement learning application for smart radio frequency spectrum sensing.
After setting up our radio system, we successfully collected real-world data and moved processing to a faster cloud GPU. To do so, the system uses a software-defined radio to capture and store signal data from the environment and handheld transceivers. The captured waveforms are run on the CFAR algorithm using Google Colab to perform computations using Google's GPUs. And it runs a Python program that utilizes a cell averaging constant false alarm rate algorithm, otherwise known as CA-CFAR. This algorithm takes a CSV file as input and has been optimized and parallelized by using Numba, a Python library.
We tested and analyzed our improvements on the algorithm for peak detection in audio recordings by measuring its execution time. We ran the algorithm 10,000 times on both the original version and an optimized version, and found that the optimized version was about 85 times faster than the original. Another series of tests we executed was testing the range of a radio sensor by using walkie-talkies at different distances. We found that the radio sensor was able to detect external frequency signals up to a range of around 2 to 3 meters, which was less than expected. While the team was successful in getting the radio to work, the limited range of the sensor was a hindrance in practical applications.
During the course of the project, our team encountered several delays caused by various issues such as waiting for supplies, troubleshooting internet conductivity, and addressing missing peripherals. Despite these challenges, we were able to quickly adapt our plans and remain within the recommended budget. We only made a few additional purchases, including a cable and handheld transceivers for testing purposes. To ensure safety and ethical compliance, the project team is also required to adhere to FCC regulations regarding specific absorption rate levels and minimize the generation of electromagnetic energy. Additionally, we must refrain from excessive transmission, accurately measure frequencies within the legal spectrum, and avoid accessing restricted channels to prevent legal, privacy, and security concerns.
Although we improved the overall efficiency of the algorithm, there are still other areas to explore and enhance. Some possible improvements, such as adding more radios to the system to simulate a more realistic environment, and automating the subsystem processes to streamline the testbed system, are a couple of these. Additionally, another improvement lies with GPU compatibility and accelerator options. Currently, the algorithm processes are on Google Colab Cloud GPU services as an alternative to a physical GPU installed into the computer. One way to speed up all processes would be to find a GPU compatible with the operating system and utilize it as an accelerator for the whole testbed system for both algorithm and the radio. This would improve the overall performance of the testbed system itself.